So we have seen how important it is to have good data quality. Now we will see how this is feasible and what we can do to increase the data quality in the end in our data set. We will start with some balance checks. Byung-ho has introduced the concept of the energy balance to you. And once you have the energy balance, you can have a look into details in the internal consistency. Some things that you will have to look out for is if one field is supposed to be the sum of two others, is it really? Does the detailed breakdown match the total? For example, this could be for trade or for demand data. Are the stock changes correctly calculated? If you have decided to calculate them in a specific convention, is this used and is this used consistently? Is the data set complete? Is there, when there is a decrease in use of one fuel, a coupling with an increase in use of another one or another explanation like efficiency improvements? And finally, in general, is the story logical? For example, if you know that your country is a big coal producer, do you see that in the energy balance? And in general, it is good practice to analyze the data processes to identify possible points of failure and introduce checks. This is, for example, with the process A, where we have extracting fields, summarizing data, reformatting data sets. So this is something quite manual. And here, one or two items could be dropped from the large data set quite quickly. So it is good to compare before and after counts and totals of data in order to make sure that you don't drop any data points, because afterwards it's going to be more complicated to identify where this is coming from. Let's introduce the data validation aspect with a quick Mentimeter question. So I'll move to the Mentimeter, go to the website that you all now know and use the code 60491269. And look at this energy balance table. This is only the supply of the energy balance table. And tell me if you see any obvious error. So here we're talking consistency. And I'm gonna show, yeah, so we have first answers coming in, total stock changes, not stock change of natural gas. It's one of the answers, then the 100, 102 biofuels. Biofuel doesn't balance. I'll wait a bit to let you have the time to have a look at this energy balance table and see if there is anything worth mentioning. Okay, we have again the mention of the stock changes, of now the trade, that this is in crude oil, I think, which is mentioned. More and more answers coming in. Yes, so we have a lot of mentions of the biofuels and of the stock changes. I'll wait a bit more because we only have 16 respondents. Okay, so I think we have quite a consensus here. I'll come back to my presentation to show the answers. So as you've correctly seen, we have a problem with the biofuels in waste. We have 100 in production. We have nothing in imports, exports, bunkers, and stock changes, but we have a 102 total energy supply. So this doesn't add up. And if we look at the total of the total energy supply, we also don't see this 2 there. So there's obviously a problem here. Then someone mentioned this as well. So it would be worth mentioning to the data provider that this seems a bit fishy. We have 2,000 KTOE as imports and the same quantity exported directly. Might this be transit? That would be something we would ask. And then we have a third point, which I think is missing on my slide here, but you correctly identified it. The stock changes of natural gas with 250 KTOE are wrongly calculated in the total, where we have only 50 KTOE in stock changes. So very nicely done. Congrats and thanks for participating. We'll continue now with the balance checks, and we will talk about statistical differences. I know that you've already discussed this with Byung-ho, but just to put it out there that this is really an aspect that helps you validate your data. Indeed, when we collect energy data, we try to get a picture of supply and demand in the market, and we would think that the market is in equilibrium, supply is equal to demand. The supply is how much is available to the internal market, the demand is how much was consumed in the market. The problem in practice is that measuring supply and demand comes with many challenges, and we often have different sources of data for the supply and the demand side. And the statistical difference basically measure the level of mismatch between the collected supply and demand data. And they can be, if they are very high, a red flag, often when it's more than 5 to 10% of the deliveries to the market. But as mentioned by Byung-ho previously, a statistical difference of 0 is also suspicious because we wouldn't want to hide the statistical difference into our data. We would want to show it to show, okay, we have different sources. This is what is coming out of it, and then try to work with the different sources to reduce the statistical difference. So what can one do? One should check the completeness and coverage of the data, review the definitions and methods of data sources, check the calorific values for supply and demand, because these could be a reason for a high statistical difference, and check if there are any new trends missing. For example, if you know that the country in the past didn't have solar PV, but it now has, maybe that is something that is missing because it wasn't integrated in the template for data collection yet. And so that's something to double check. Then another aspect to look at is the on-use and the losses, especially for electricity. These are values that shouldn't vary too much across time. The on-use of electricity by power plants, that's the proportion, that's the electricity, used by power plants to function, basically. And it's not expected to vary significantly year on year. We would say maybe around 3%. And if in your country it has been for the whole time series higher or lower, as long as you can explain it, that's fine. But what we would ask about, what we would try to flag, is if we have a very big peak or a very big decrease. For example, in the graph here, in the dark blue line, we see that around 1994, we have a peak in the on-use, and around 2005, we have a drop. This is something that we would want to ask what happened there. The same for the transmission and distribution losses. This is the electricity that is lost during on the way, basically, to the consumer. And here as well, we would say that the technical transmission and distribution losses should stay below 10%. It could be that those go higher if we have problems with the maintenance of the grid or problems with theft. But again, here it's important to explain these differences. I'm coming now to the calorific values. So calorific values, as you've seen before, are essential to build an energy balance as they convert from the physical to energy units. And for every energy product, we expect to have the calorific values in a specific range. Coal calorific values won't have the same range as gas calorific values, for example. And so it's good as a first validation to compare the collected calorific values against the default. It's also good to have a look at the historical calorific values for the product, as they can be region specific. You have on the right, on the bottom right of the slide, an example where you see that depending on the region, we really have quite a strong difference. So this is New Zealand and Kazakhstan. Yeah, and last but not least, check if the calorific value used for consumption is in line with the one used for supply. If it is not, this might lead to statistical differences. Then, to analyze the time series, it is very useful to compute growth rates. I think all of you might already have done this. A growth rate is computed quite easily by taking the current period minus the previous period and divide it by the previous period. And to have it in percent, we multiply by 100. This involves comparing the data point of the latest period to that of the preceding periods. And this can be very useful to see if there was any unexpected trend. It is important to note that when the seasonality is strong, or we are dealing with monthly data, it makes more sense to compare the current months with the same months of the previous year, just to be sure to compare apples with apples. And this is a comparison that is very useful for production, for consumption, but less so for stocks and trade that are very variable. Then we will try to make sure that the data set is coherent, that it matches the expectations for trends. For example, if we know there is a maintenance or weather disruption, do we see this in the data? Then some patterns may be fuel specific. For example, we see it here in the right graph. Sweden imports much more natural gas in the winter months because that's when there is more demand for heating because there are colder temperatures. So there is a seasonal trend in the natural gas imports in Sweden, and we would want to see this reflected in the data. Oil and gas fields, as another example, follow cyclical maintenance patterns. So this is also something to consider. And then we would want to check in our questionnaire if the data is matching similar data in another questionnaire. For example, if we have an input of natural gas to electricity, does it match the one reported in the electricity questionnaire? And last but not least, in most cases, among the different variables, there are relationships, and we would want to satisfy them. For example, if inputs are increasing, we would expect the outputs to increase as well. And if that's not the case, we would want to be sure that this is a result of something that we can explain, for example, improved efficiency. So then we can compute the efficiency to make sure this is the case. Let's talk now about breaks in time series. They can happen when the coverage improves or the methodology changes, but in general, we would aim for a consistent time series. And each time you have an unexplained break or a big change in the trend, we would want to explain this. Breaks in stocks, for example, also are rare and should be investigated. And for certain flows, they are more consistent over time. And in these cases, sudden increases or decreases should raise a red flag. And in that case, we would consider going back to the data provider and ask what is the reason of this break. We have a good example in the right side of the graph, the right side in the bottom, the refinery intake in barrels per day. So we have the time on the x-axis, and we see two big outliers. One is in April 2005. This is much lower, and one in December 2005, much higher. The first one, the lower refinery intake, could be explained if the refinery was in maintenance at that time. However, the other one, the December 2005 one, is much more difficult to explain because a refinery intake in a refinery is usually quite constant because the refinery has been calibrated for a specific intake and cannot take more than that. So that would be really something that we would want to ask and check if there is not a problem with this data point. I've mentioned efficiencies before. We will have a look now at how they can help us validate the data. For every energy transformation process, you have an input and an output. And there is a relationship between these that will depend on the technology used. If we check this, we ensure the consistency of our data set and we ensure that the relationships are satisfied. The efficiency is calculated as the total useful output over the total input. And this should always be in net energy units. For example, if we have a transformation process of fuel to electricity with the inputs A and B both in terajoule and the output C in terajoule, the efficiency will be calculated as C over A plus B, whereby, important to note, it should be the same energy unit and the same energy form, so net or gross. Then, once we have computed the efficiency, we will be able to check it against the expected ranges for the process and technology. The first point is, if you have an efficiency larger than 100%, that's very implausible. Then we will look at the ranges. They can be dependent on the type of plant and on the fuel used. And they will vary depending on the state of technology. An older plant will usually have a lower efficiency. And they should not vary significantly from year to year because technology upgrades are time and capital intensive. So except if you have a new power plant coming online, and then you should see an increase in efficiency, you should have a quite consistent time series in the efficiencies. Let's put this into practice and go back to our Mentimeter. Up. I'll go, yes. So the question is, what is the efficiency of the refinery? I'll show you the image for a while. So you have here an extract of the energy balance where we only see the transformation sector. And if you go to the line oil refineries, you will be able to find the information you need to compute the efficiency of the refinery. So I leave you some time. I hope everyone found the code. So it's 60491269. I see first questions coming in. I will share them in a minute, just keeping the table for now so that it's easier for you. So we have several answers. The majority is saying 105%. No one is saying 100%. We have a few people for 95%. Very few for 80%. Answers keep coming in. Okay, so a majority is voting for the 105%, but quite a few people also answered 95%. So we'll have a look. The correct answer was 105%, and I will explain now why. So the correct answer is 105%, because the efficiency is calculated as the output. The output here is the 10,000 kTOE divided by the input, which is the 9,500 kTOE. Here, as we are in an energy balance format, we already have the right units. We don't need to convert anything. We have an energy unit and it's all in net calorific basis. So we only need to take the output, 10,000, divided by the input, 9,500, which gives us the 105% efficiency. So as is mentioned in this slide, this would raise a flag because we show refinery gains in energy term, which is not possible. So this is something we would go back to the data provider or first check in our data if we didn't make a mistake, for example, in the conversion factors. So I'm going to now talk about the use of different data sources and data sets, which can help you try and identify and consistency in your data. First of all, note that there are different product classifications. Goods can indeed be classified using 3 systems: the harmonized system, the standard international energy product classification, or the central product classification. And if you have different sources that report using different product classifications and you don't adjust, this can lead to discrepancies in data. Then it is good, if you have the data, to mirror checks. Particularly useful for data sets with a bilateral component. This could be, for example, for trade, as you see on the right graph. Here we have the electricity trade, always from country A to country B, but reported one time by country A, so this is the blue line, and one time by country B, this is the red line. We see that over the years, it has always been quite consistent. And then at the end, we have a big break, a big difference between the 2 countries. So this is something where we would go and try to identify what is the problem here. This is something we can help you with. If you want to identify partner countries, we can try and help you work with them to mirror the trade data. Then on the granularity, it is very helpful sometimes to have monthly data in order to validate the annual data. You can check if the aggregate of the monthly or quarterly data makes sense with the annual data, and watch out, of course, for difference in coverage and definitions. So here in the example, we have LPG. The green is the monthly and the blue is the annual. We see that for 3 years, the data was quite consistent, with the annual always being a bit higher. This can be explained quite easily if we have coverage problems as the monthly data is collected in a quicker way, with less time lag. It might be more difficult, to have a complete coverage of the country's data. So that's explainable. What we see though in 2016 is that we have a real drop between the annual and the monthly. So that's something we would watch out for. And then economic data can also be useful to show you how consistent the data is and to try to explain some events. For example, when the financial crisis in 2009 happened, this was really visible both in the energy data and in the GDP data. And so you could really explain this by looking at the 2 data sets. Last but not least, if you don't have the data, you might need to estimate some missing data. Of course, we always prefer to have the data that is submitted being real observed data. But if you don't have one data point, a small proportion of the balance, it is possible to estimate it. Estimation should only be used for a short time, whilst you prepare a system of data collection using the steps that Louis mentioned before. And then the strategies will depend on whether the data needs to be systematically estimated or if a data point is missing exceptionally. And of course, whenever a data point is estimated, this should be clearly marked, and the metadata should give more information about that. In general, when we estimate a missing data point, we should ask the following questions. First of all, how important is the flow or the product? Then, is it correlated with another flow for which there is data? This might help you to make an accurate estimation. Is there a seasonal or historical trend? Here again, if you have very clear pattern, it might be easier to estimate. And then, why may this period be different? If you use for 2020 estimations, the pattern of the years before, you might not have a correct estimation because of the COVID-19 crisis. And then, can market trends be used as an indication? So basically, really try to make a scope of all the information available out there to help you do an accurate estimation. Last but not least, recommendations and assistance. I'll quickly talk about some items that can help you when you do your data collection and validation. So first of all, we would recommend that You should have a solid legal foundation for your data collection system. You should establish a network of different institutions that you work with, both with members of national energy statistics and with partnerships outside the ministries, secondary data sources, etc. We've seen that a lot of you already work with several institutions around the world. Then one should build up formal procedures to support confidentiality, to protect the data, but also to get access to the data. Establish a data collection strategy. Provide up-to-date metadata so that the user can understand what is behind the numbers. And implement international standards and concepts to have comparability. You can see some examples of how other countries do it in the country practices database, which is regrouping all kinds of methodologies. So surveys, modeling, measuring, administrative sources used by the countries. And you can, of course, also share your own expertise if you see that it's not there. Yeah, this is an example of how it's used. For example, if we want to see residential surveys, we can go to this country practice database, and then we'll have a list of all the countries that have implemented and shared their practice and how they did it. For example, here we have the survey used by Canada, and this is really an example of how one can benefit from each other's work and try to exchange on best practices. Finally, beyond data collection, we have a lot of data disseminated. We have data services for purchase, but if you go on our website, you can also find a lot of data available for free. And all the data that we produce is feeding in the different reports of the agency. So the World Energy Outlook, the Global Energy Review, different market reports, COVID-19 impact on electricity reports, etc. So I'll invite you to have a look at our website